Welcome to this explainer. Okay, if you're gearing up for the Cambridge IGCSE physics exams, we're diving into a totally crucial part of the 0625 syllabus today: alpha, beta, and gamma radiation. Looking through the data, it's actually fascinating to see how mastering this specific subject matter is literally what separates average scores from those truly standout performances. So let's unpack exactly what the examiners are looking for, shall we?
Okay, let's dive right into this because when we look at our source data, this topic is, well, it's completely unavoidable. Questions on this appear in literally every single examination series. No exceptions. So mastering this, it isn't just a good idea, it's an absolutely essential foundation for your success. Think of today's roadmap as your exam hacker's blueprint. We'll start with core radiation principles, then move into systematic problem solving, followed by some critical examiner warnings, and finally wrap up with your final exam strategy. Let's kick things off with Section 1, Core Radiation Principles. Now, the Cambridge syllabus makes it crystal clear. Top-performing students absolutely must have a connected, conceptual understanding of this stuff, especially when applying these principles to completely unfamiliar contexts. And the absolute bedrock of radioactive decay rests on two very specific words: spontaneous and random. Getting these precise definitions locked in is your golden ticket to higher marks. So, spontaneous means the decay process happens entirely on its own. It's completely unaffected by external factors, like temperature, pressure, or chemical reactions. And random? That means it's fundamentally impossible to predict exactly which nucleus in a sample is going to decay next, or exactly when that decay will even happen. Trust me, examiners aggressively look for these two precise terms when they're grading your foundational knowledge. And this brilliantly illustrates how we categorize these emissions. It's really like looking at a fascinating trade-off between power and penetration. Take alpha particles, for instance. They're essentially just naked helium nuclei, super heavy and highly ionizing. But because they're so bulky, they're stopped by a mere sheet of paper. Then we have beta particles. These are fast-moving electrons, so they pack moderate ionizing and penetrating power, and they're usually stopped by just a few millimeters of aluminum. Finally, gamma rays. These are high-frequency electromagnetic waves. They're very weakly ionizing, but wow, are they highly penetrating. You need thick lead or concrete to significantly reduce their intensity. Now, here's a secret. Principal examiner reports consistently highlight that candidates who make cross-topic connections achieve significantly higher marks. So, here's a highly effective memory hack for you. Create a personalized acronym right now to anchor these differences in mass, charge, ionizing ability, and penetration. Building that active mental link today is going to save you vital minutes when you're sweating under the pressure of the exam clock. Okay, moving right along to Section 2, Systematic Problem Solving. We are shifting gears now from passively absorbing physics facts to actively executing exam strategies. When you're staring down a complex radiation problem, using a standardized sequence is an absolute lifesaver. Step 1, deconstruct the question and extract your data. You've got to identify the givens and the unknowns first. Step 2, solve systematically. Choose an analytical framework and use clear, undeniable notation. And Step 3, evaluate your results. Check for reasonableness. Actually ask yourself, does this final answer actually make sense in the real world of physics? So the crucial point here is that the assessment framework prioritizes analytical depth over superficial breadth. We call this the method mark strategy. Examiners frequently award marks for the process itself, not just for magically guessing the right final number. It's all about meticulously proving your logical, structured reasoning right there on the paper, showing the examiner exactly how you reached a conclusion, using the correct formats and appropriate terminology at every single step. That is what truly earns the big points. Next up, Section 3, Critical Examiner Warnings. Let's see what the graders are actually saying behind the scenes. Pulling specific data straight from the principal examiner reports of past exam series, we found something huge. The examiners have identified exactly 3 major pitfalls that consistently derail candidates. And here are those top 3 pitfalls. Number 1, answers are just way too vague. Examiners are hunting for specific details, not broad generalizations, which means superficial breadth tends to get penalized. Number 2, format and presentation are entirely forgotten in the rush to just get an answer down. Believe me, strict conventions like proper headings and clear annotations really do matter. And number 3, answers are frequently not specific to the context given in the question. Just reciting a memorized textbook definition won't yield full marks if you don't apply it directly to the unique scenario the question is asking about.
This is a fascinating and honestly critical insight from the reports. Candidates constantly confuse key terminology. Consider this a high alert warning. Eliminating vague language and actually defining specific terms before you apply them to the context is a surefire way to show examiners your true conceptual depth. It proves to them that your answer isn't just a bunch of repeated words, but actually stems from a deep, rock-solid understanding.
Now, when a question asks you to evaluate or compare, the ideal formula goes way beyond just listing facts side by side. The real secret to success requires explicitly identifying both similarities and differences. You need to use comparative connectives, words like whereas or conversely. It's also absolutely vital to support each comparison with actual evidence from the data they've provided, and finally, to draw actual conclusions about their relative importance. This is what true evaluative thinking looks like, and honestly, it aligns perfectly with top marks.
Let's move to Section 4, Final Exam Strategy, and see how all of this builds together. To bring all of this together, I want to leave you with a final, slightly provocative question. When you sit down in that exam hall, are you just going to list off memorized physics facts, or will you actively prove your analytical process to the examiner? Taking these structured frameworks, deconstructing the context, defining your terms, and systematically evaluating your answers, and rigorously applying them to past papers is literally the ultimate way to capture every single possible mark. Good luck out there.